All right, so today we're going to take a look at 11.5, which is lines and planes in space. And we're going to first give a definition for how we think about lines in space. So as with lines in a plane, we can specify a line by identifying 2 points on the line, or 1 point and the direction, i.e. the slope of the line. There's 2 ways to represent the equation of lines in space: parametric and symmetric. These are the 2 different forms, I guess, for these lines. Parametric looks like x equals x1 plus a1t, y equals y1 plus a2t, z equals z1 plus a3t. And these are for the point, x1, y1, z1, because it said we need a point, and we need direction. So the direction for the vector, or the direction vector, is a1, a2, a3. And if you're given 2 points, you could create that vector, which I think we have an example that's going to do that, and then do the same thing. The third one is a symmetric form of line, and it does look like, and it is in fact, a triple inequality: x minus x1 over a1, y minus y1 over a2, and then z minus z1 over a3. And if you take a look at the representation between these two, what you'll see is that if you solved each one of these for t, let me get that back there. Okay, if you take each of these and solve them for t, they create what's showing up in the symmetric form below. So each one of those is really just set equal to t, so they're set equal to one another. Okay, ready to do an example? Okay, it's going to do exactly what I had just said. It's going to give us 2 points, and we're going to find the parametric and the symmetric equations of the line. So the forms themselves are set up using a point and a vector, and the vector is the direction vector. These are not giving us a direction vector, but you know how to get a vector between 2 points. So that's what we're going to do first. So the first thing we're going to do, we'll call it A just because they did, not because it really matters. But we're going to find the direction vector. And the order in which you subtract doesn't matter, but I'm just going to do the second one minus the first one, and I'll write it out clearly. So this is 2 minus 0, 0 minus 2, and then 2 minus 1. So we've done this now for going on a week and a half thereabouts, maybe more. So we're going to find this vector to be what? Good. 2, negative 2, 1. Okay, is that right? So now that we have a vector, and you can choose whichever point you'd like. I'm just going to use the first one. We can create both types of both forms of the lines we mentioned on the previous slide. So the first one says parametric in terms of part A, so we will do parametric first. So parametric, the first one will be x. So x is 0 plus 2t, direction 0, point 0, direction 2. There we go. Y is equal to 2 minus 2t, point 2, direction negative 2. And then the z is going to be equal to 1 plus t. Yes?
Why do you have 2t there? You get the 2.
They're coming from over here.
Oh.
So the second component. So this is the first component. 2 is going in here. The second component's 2 is going in here, and then the 1 is going in here.
Okay.
Yeah, that's where those coefficients are coming from. So all those coefficients, is kind of messy looking here. This is a 1, come from the direction, and then all of the points at the beginning are coming from, I chose the first point. You could have chosen the second point just fine. It would have created a equal kind of statement. So, okay, everybody good with that? Okay, and then we can find the the symmetric form as well. So B is the symmetric. And for symmetric, we have x minus the x value, which was 0, divided by the slope value, which was 2, or the direction vector's value, right? equals y minus 2, the y coordinate value, divided by the y's slope, which is negative 2. And then z minus the z value, which is 1, divided by the direction value, which is 1. And these are two different forms for this line. Okay, straightforward enough? Just an application of a definition. Okay, so another definition then. We're going to let L1 and L2 be lines in space with directions A and B. L1 and L2 are going to be parallel whenever the direction vectors are parallel. That kind of makes sense, right? That's how we decide if lines in 2 dimensions are parallel, if their slopes are equal, right? Their slopes are equal means that they're going to be parallel, and so the lines then would be parallel. 2, it says if L1 intersects L2, then A, the angle between L1 and L2, theta, is the same as the angle between A and B. Again, that should make sense, right? Their direction is being determined by these direction vectors. So whatever angle is happening for the lines is the same as the angle that's happening for the direction vectors. And B says that if they are orthogonal, which would mean that they're forming these 90-degree angles, right, or right angles, then the direction vectors would have also been orthogonal. Again, those are very reasonable kind of statements. And it's a definition. It's not a theorem or a proof, right? Like, it's not a theorem that needs to be proved. It's actually definitionally these things all just pan out, right? The way we would expect. All right, so we're going to determine whether the lines are parallel, skew, or intersect. Now, we didn't actually define skew, but you've probably seen it in a geometry course or something before. So I think we all have a pretty good idea of what parallel means, right? They run side by side, like railroad tracks. Intersect, you know what that means, they cross. What does skew mean? Because skew didn't happen in 2 dimensions. Most of the things we do in life mathematically up to this point have been 2 dimensions. What is skew? Have you seen it before? Has anybody, I won't point out and make you say anything, but have you seen it before? Okay, we've got a couple nods, maybes. Okay, let me give you 2 lines in our classroom that are skew. Okay, so we're going to go with a ceiling line up here where the ceiling and the wall meet. Everybody's got that picture in mind, right? And you can see lots of parallel lines to that line. The tray of the chalkboard would be parallel, right? The line along the floor and the wall would be parallel. Everybody's good with that, yeah? And you can see what intersections would like. An intersection would be like the corner up here. So the line along the ceiling and the line for the side of the board and the line along the ceiling on the top, the backboard right behind me, those would intersect. So those would be intersections, right? An intersecting line. But if we take that same line at the top that I've mentioned before and we look at this chalkboard tray right here, right? They're not parallel, but then neither do they intersect, correct? Like that can't happen in 2 dimensions, but it does have the ability to happen in 3 dimensions. Is everybody tracking okay with that? Those are the only 3 possibilities. They're either parallel, they intersect, or they're skew. But we do have a third possibility, that is the skew part, that we haven't had in 2 dimensions before. Okay, all good so far? Okay, so we're going to decide if these are parallel, skew, or intersect. And there's not a test that says, hey, these are skew. That's the third default when the other 2 don't happen. Y'all with me? Okay, so taking a look at these, when we're trying to decide if they're parallel, over here it talked about deciding if they're parallel based on their direction vectors, right? If the direction vectors are the same or are constant multiples of each other, then they are going to actually be parallel, and so then the lines themselves will be parallel. So we need to find the direction vectors. So looking at these, what is the direction vector for each one of these? Let's do this first one, I'll write it underneath. Over here, how did we find the direction vector? Well, we took the difference in the y values, right? And where did those difference in the y values, that direction vector, go? In front of t. Okay, the direction vector is going like a slope. It's acting like the slope in front of t. Okay, everybody good? Okay, now think about it from this perspective where you're given a line. The direction vector is still going to be the values in front of t. So what are the values in front of t on our first line that's given? Yeah, 1, 0, and 2. And what are they going to be for the second line given? 2, 2, and 4. Okay, is that all right? Okay, Are these vectors parallel? No, they're not parallel. Okay, and remember the reason that they're not parallel, so we can say yes. Let's give them names. Let me call this vector 1 and vector 2. You can call them V and W. Call them whatever you'd like, but I would like to be able to reference them, so I'm going to call mine V1 and V2. So V1 is not parallel to V2. Right, you do the parallel line, you put a slash through it, just like you do not equals. Okay, it's not parallel to V2. And it's exactly what you just said, Adrian. Say that again louder.
They have to be multiples of one another.
Because V1 and V2 are not scalar multiples. Okay, so we've eliminated one of the possibilities. They are not parallel. All right, so how do we figure out if they intersect? Well, notice here, when we created these two lines, or they were given to us, but when they were created anyway, one has this parametric variable t, and the other has the parametric variable s, right? We don't want to have any illusion that the parametric variables are the same, and that's why they're labeled differently. They're not exactly a dummy variable, but they're kind of acting like that. They're another variable that we want to recognize as not being the same from one line to the next. So over in the first line, we have t happening, right, as our variable, and in the second one, we have s happening as our variable. Everybody good so far? Okay, so what we're taking a look for then is we're look for, or what we're wanting to find, I should say this way, is any location where we can have a t and an s that are going to match. They don't have to be the same, but if they match, then we're going to have lines that intersect. So we try to look for places that happens, and we do that like this. So let me put this line here to indicate we've already checked the first half. So then we're going to take a look at x, and we're going to set the x values equal to one another. Okay, we want the x's to match, we want the y's to match, we want the z's to match. And so we're looking for an s and a t value that make that happen. Maybe that's a better way to describe it. So if the x's are going to match, I need 4 plus t to equal 2 plus 2s. So that's all right? We could solve that, but it doesn't give me a single value for t or s because it's one equation, it's two unknowns. I can do the same thing with y. So for y is a little easier to work with because y only has one variable. 2 would have to equal 2s, right? Yes. We can figure out what s is now, can't we? So what is s? Yeah, s would be 1 based on this. So if I take this first equation now and I make s equal to 1, I can solve for t. Notice I haven't done anything with z yet. We'll get there in a minute. But right now I can work without it. So I have 4 plus t equals 2 plus, and it's supposed to be 2 times 1. So what will t equal with all of this going on? T is 0. Okay, so s and t aren't the same. That's okay. But what we want to see is we want to see what happens with z. Will the s value of 1 and the t value of 0 actually work in the equation for z? And if they do, then we've got something that intersects. So in z, we have 3 plus 2t equals negative 1 plus 4s. And we want to see if we can make them equal to one another at the same location where s and t show up equal. Not equal, but show up having the x's and the y's equal. So I have t is 0 and s is 1. On the left I have what? 3. And on the right I have 3. So this worked, correct? So at the s value, keep getting it backwards, the s value of 1 and a t value of 0, the ordered pairs for x, y, z match, right? So what does that mean? It means they intersect, right? They're going to intersect, specifically at the s value, keep doing it, an s value of 1 and the t value of 0. So these are going to intersect, and we'll write that description down over here. Correct. So they intersect when s is equal to 1, t is equal to 0. And we can figure out what that value would be, write the ordered pair for it. When s is equal to 1, so just pick, we'll use s is equal to 1 and we'll just use this. But if s is equal to 1, what's x? 4. If s is equal to 1, what is y? 2. And if x is equal to 1, what is z? 3 again, right? And you could likewise put t in at 0 if you want. So if I put t in at 0, I better get the same 3 numbers. Like, that's the whole point. If I put t in as 0, I get 4, 2, and then 3. Is that the same thing? It is. It's always good when it works out nicely. So they intersect, and so they would be intersecting at the ordered triple 4, 2, 3. And just like Adrian pointed out, and we were about to get to too, if we had not found this, like at this step right here, if when I did z, I used the s and the t that I had found, and I put them in, and the two sides weren't equal for z, then these lines would be skew. Okay? Because the x's and the y's were already coordinating, but the z didn't coordinate with them. Right?
Will it only ever be one of those three?
Yes, it can only be one of those 3. These are mutually exclusive categories. They cannot match up with 2 things. And if you think about it, you can take 2 of them if you wish, and think about my imagery in the classroom. Can it be parallel and also intersect? Well, no, definitionally, that's kind of contradictory information. And the same is true for skew, even if you haven't really done much with it before. Yeah. Okay, any questions? Okay, so these are lines in space. We did lines on my walls. The other half of this is planes in space. So a plane in space is determined by specifying a non-zero vector n, which has components a, b, c, that is normal to the plane. So the word normal means that it is orthogonal. Remember, that's perpendicular to every vector lying in the plane. And we have this point P, or point, they've got x1, y1, z1 lying in the plane. And the equation then is going to be a times x minus x1, b times y minus y1, and c times z minus z1, which equals 0. Or if you multiply that out and collect all the constants, you're going to get ax plus by plus cz equals some constant d. Or you could put the d on the other side, right? There's going to be some constant that these are going to all flush out. And we have this equation. So your plane that you should be picturing is like the wall, right? So in terms of our classroom, the line is where my wall and my ceiling met, but the plane itself is the wall and the ceiling, right? Those are planes in the perspective of what we're looking at. And we're going to find equations for planes. That's what we're going to do next, just like we found equations for lines. Are you ready? Okay, now it talks about this idea of being a normal vector. It is orthogonal. And you just did a section of homework about things that are orthogonal. And what came about? What process were you working on in section 3? 4? What did we just finish? 4. Section 4. No? Cross product. We were looking for cross products. So this is going to lead us into cross products as well. We're going back into that. Okay. So we have an equation we're finding an equation, of a given plane. We have 3 points. So if we have 3 points, we can do lots of things, right? We can use any of the 3 of them in a moment to represent this x1, y1, z1. So we'll get to pick that. If there's one of them that's preferable, maybe because it's got a 0 in it, I kind of like the middle one. That's nice, it's got a 0 in it. You might choose that one. If you just want to choose the first one because it's the first one, you can do that, doesn't matter. You can also find vectors, right? You can find a vector between any 2 of those points, right? I can take point 1 and point 2 and I can find the vector that is between them, right? That's the direction of that ordered pair if you were to attach those 2 points together. We can do the same thing for the second one and the third one, or the first one and the third one, right? Okay, I would like to give these points some names so that we can all call them the same thing. So I'm going to call them P, Q, and R. Okay? And we're going to do just that. We are going to find a vector given 2 of these points at a time. I'm going to go with what I have on my paper. That way, if we make a mistake, we'll be able to catch it easier. But you can pick any 2 points you want to create the vector. I'm going to choose to create the vector PQ and the vector PR. If you want to be very adventurous and do QR and then check and see if you get the same thing we do at the end, feel free to do so. All right, PQ. So I'm going to take the points Q and I'm going to subtract off the point P. So I have 2 minus 1, negative 1 minus negative 2, and 0 minus 1, which will give me 1, 1, negative 1. Did I get that right? That's what I have written down. Okay, so PR is going to take the ending point R and go back to P. And so I have 3 minus 1, negative 2 minus negative 2, and 2 minus 1. So the first one is 2, second one is 0, and then the last one is 1. Okay, everybody good so far? We've got the direction between two pairs of these points. All right, the next thing we're going to do is we're going to find the cross product, because the whole point in finding the cross product is that we're able to find the normal vector that we've been talking about. I need a normal vector. I can find a normal vector by taking any two vectors and then finding their cross product. So in theory, because we're doing it all together unless somebody is being adventurous, if we use any of these two vectors, we will both, you and whoever else, me and whoever else is doing it, get the same normal vector no matter which two original vectors we chose. Are you with me on that? Not only that, but I chose the vector PQ, and if you chose the vector QP, it would be the same too. Right, so we have three separate vectors, but we have directions on all three of those vectors that could be flipped around, and it would be okay too. So we're going to find the cross product of PQ and PR. So PQ cross with PR. And we haven't done one yet today, so we'll be real clear. I, J, and K. And we have 1, 1, negative 1, 2, 0, 1. And we have our vector at I. So remember, we're using the bottom coordinate, or corner rather, down here. And so I'm going to write them all out just in case it's been a weekend since you've done them. So this is 1, 0, negative 1, 1, minus J. I'm doing the outside pieces here and here. So I have 1, 2, negative 1, 1, plus K. And then I'm doing this corner over here. So I have 1, 1, or 1, 2, 2, 1, 2, 1, 0. Okay, I think I got them all there. And then we're going to do the determinant for each one. So if I come down and then back up, that just gives me 1. So this is going to be 1I, or just I in a minute. If I go down, this is going to be 1 minus negative 2. So what is 1 minus negative 2? 3, right?
Yeah.
Okay. And there's a negative because of the negative in front of the J. Okay. Plus, and then on the K one over here, we're going to go down. That's 0 minus what's up. That's a negative 2 then, because I'm subtracting. So I have minus 2K. So I'm going to erase the 1 since it's not really necessary at the beginning here. So the normal vector is what I just found, and they called it n, so we will too. The normal vector is I minus 3j minus 2k, or if you prefer to write it, you can write it as 1, negative 3, negative 2. Out of space. There we go. Okay, so far so good? So over here it says I'm going to take that normal vector. The normal vector's components that I just got are the A, the B, and the C here. Okay? And then my x1, y1, z1 are any of the 3 points that I would like to use from what I was given. So we'll deviate from what I've got written down. Which point would you like to use? P, Q, or R? Somebody pick one.
Q.
Q, thank you. Q is great. We're going to use Q. So when we find this, we're going to take the normal vector's x component, or I component, which is 1, and we're going to multiply it by x minus the x value at Q, which is 2, plus. And then we're going to get the normal vector's j component, which is negative 3, so that's actually minus 3, times y minus the y component, which is negative 1, so this is y plus 1. And then I have the z component, so it's minus 2, and z is 0, so it's z minus 0. This is the line. That's all well and good. We're going to clean it up some. We're going to actually flush it out to the point where it looks like this one at the bottom all cleaned up. Okay? So do some distributing and combining like terms, that sort of thing. All right, so I have x minus 2 minus 3y minus 3 minus 2z equals 0. That gives me x minus 3y minus 2z. And what constant do I get? What are the constants over there?
-5.
Yeah, -2 and -3, so I have -5, you bet. -5, it equals 0. This is the equation of the plane. And I'll have you know, on my notes, I actually used point P apparently, and that's still the same equation for the plane that I got. So we've verified it at least with a little bit of variation between what I did before and what we did in class now. Okay, so any point we use will be fine. And we can create any of the vectors we mentioned before to do that. Okay, so you're going to really like the next one. Do you know what it is about the directions that you're going to really like? The sketch. We're going to try anyway, right? We're all going to have some grace with the trying of sketching. It says find all intercepts, and sketch the given plane. Okay, the finding of the intercepts is not that big of a deal. Okay, we can do that just fine. The sketch part's a little bit fuzzy, and we'll be careful with that. All right, so we're going to first find the x-intercept, y-intercept, and z-intercept. So do you remember how you find x-intercepts when you're just working in 2 dimensions? What do? Let's think about a picture real quick. Say it again, Sophia. Yeah, it's when y is equal to 0. So we'll think about a 2-dimensional plane. So it is an x-intercept, say right here, because the y value is equal to 0. So 3-dimensionalize that then. If I want the x-intercept in 3 dimensions, what would I need to find? Yeah, y would be 0 and z would be 0, okay? So this is our image of what we're looking for over here in 2 dimensions that we're 3-dimensionalizing. So if the x-intercept is what we're looking for, our y is 0 and our z is 0. And if we come back up here to the plane that we are given and we let the y be 0 and the z be 0, we get 2x is equal to 4, or x is what? 2. So this is an intercept, which means it's a point, which means an ordered triple. X is 2, y is 0, z is 0. This is the x-intercepts form. So what would we do then for the y-intercept?
Same thing with x.
Yeah, same thing, but with x and z. So x is now 0. The y value is what we have, and the z value is 0. Okay, so what will y equal with a little bit of simplification here? Yep, -4, very good. And so the ordered triple is 0, -4, 0. And a z-intercept would mean x and y are both 0. So x is 0, y is 0. What is z? Just 1. So this is the ordered triple 0, 0, 1. Okay, the finding of the 3, that's okay, I think, yeah? You all seemed pretty good with that. Let's see what happens when we talk about a sketch. So I'm going to make this, I don't know if I have another slide, I don't. Okay, let me make this a little bit smaller so that we can move it to the side and talk about a sketch. So remember when we were drawing in 3 dimensions, the standard way that you see this drawn is sort of at an angle like so. The x is on the left-hand side, the y is on the right-hand side, and the z is on top. Okay? If you choose to label them differently, it's not wrong. You're just not going to see a matching image to the way you've labeled them if you're looking at like another resource. Each of these actually tells us the location where it crosses. So on the first one, x is 2. So I'm going to come out here, +2, and I'm going to plot a point, because this is the location where the x is crossing the x-axis. Let's skip the y is 4 for a second, and let's do the z one. The z is supposed to be at 1, so we would go up 1. And we'd be right here. Okay? Now, how are we going to do this negative business? I mean, if this said y is 4, we would just be out here, right? But it's not y is 4, it's y is negative 4, so where are we going to be? We're going to be back over here somewhere, right? So we need to draw this sort of in reverse. So I'm going to draw it dotted to go backwards, just so that we can try and remember that we've got that three-dimensionalness going on. Does that look pretty okay dotted for you guys still? Or does it look solid, like it's filled in? You're telling me nothing, so I think it means it looks like it's at least filled in. Let's try this one a little thicker. How about that? That's definitely dotted. Okay.
Yeah.
And we're going to go backwards, right? 4. So on that dotted part. 1, 2, 3, and 4. And we're going to put a dot there. And the best that we can do in terms of drawing this in 3 dimensions is to connect those 3 points. Okay? So we're going to connect those 3 points. This will create, obviously, a triangle. But the triangle lies, the plane, no, I said that right. The triangle will lie in the plane that we're trying to create. So the lines that we're going to connect, I'll do them like this, would be connecting these points right here together. So we have a triangle that we're forming, but that triangle is actually going to be contained in the plane that we're trying to draw. And that's the best that we're going to do. Now, that means that sort of that the point for the y is sort of coming back behind the screen, if you will, right? That's the y-intercept over here. The x-intercept's out here, and we've got this point up here, for z. Okay, so that's the points that are connecting. And this is about the best I can do to draw them anyway. So. Okay, you all good with that? All right, one more example. We're going to decide if the lines are parallel, perpendicular, or neither. Okay, so we're going to first, in order to decide if things are parallel, do the same thing that we did before. How did we decide if we had parallel lines a moment ago? What did we do? You flip back, I think it's example 3. 2, example 2, my apologies. How did we decide if the lines were parallel? What had to be multiples of each other, though? We had to find the vector. We need direction vectors. Yes, sir.
Is that supposed to be x?
Yes, it is. Let's fix that. Thank you.
I was confused.
Is it right on your paper? Oh, it's wrong on your paper, too. Well, at least it's consistent. Okay. I'll fix them both later. Okay, so it's supposed to be x. Yes, thank you very much, Ben. All right, so we've got x, y, and z, and we need to find the vectors associated with each one of them. And so we will call it a and b for the vectors. You can call them whatever you want. What is the vector for the line that's given in the first part of question 5? Oh, there's a typo again as well. This 6 at the end is supposed to say t. Does it say it right on your paper either?
Yeah, it says it right.
It says on your right paper. So that one's right on the paper. I got one piece fixed, but not the other piece. Okay. Alrighty then. One more time. What's the vector?
-3.
Thank you. -3, 4, 1. And how about vector B? 2, -2, 1. Okay. What can you tell me about those vectors? Not parallel, right? They're not scalar multiples of each other. So we're going to say that A does not equal some scalar multiple C times B. This would be notation for it. You're welcome to write it in words. It doesn't have to be written in notation. So this is true for any scalar C. So they are not, I'll use it this way. They are not parallel. Okay, so we're supposed to then try to figure out if they're perpendicular. So how do we decide if something is perpendicular? That's a little bit different question than we were asked on the other question. The other question asked about intersecting. So here, it's not enough to show if they're intersecting. We need to know specifically if they're perpendicular to each other. So how could we do that?
Would be a diagonal because
So they would be yes, we're looking at something that would be orthogonal, correct? Because we're talking about 3 dimensions. But you can actually be perpendicular because 2 lines could lie in the same plane as well, and they would actually have the word perpendicular. Dylan?
check the angle between vectors.
Yeah. Do you remember the formula for that?
It's u dot v over the magnitude of both.
Yeah. So we're going to have cosine of theta and this is what you're remembering. I'm going to use my A and B because I called them A and B, so it's A dot B over, and then you remembered correctly, you've got the magnitude of A times the magnitude of B. So that theta is what we're looking for. If theta is going to be 90, then we're going to have something that's orthogonal. And if it's not 90, then it's not going to be orthogonal, and it'll be neither. Okay? So we're going to take a look at this. Well, we have A and B. We haven't done a dot product today, so we should. What's the dot product going to be for A and B? We have negative 3 times 2 plus 4 times negative 2 plus 1 times 1. So that's my dot product. In fact, I think let me do that to the side, and we'll put them all together in a second. So this is the dot product part that's on top. What does that give me? Yep, that's what I thought I had too. Negative 13. Does everybody have that for the dot product? Okay, now we need the magnitude of A, and we'll do the magnitude of B next. So the magnitude of A means we square each component and then square root, right? So I have the square root of 3 squared plus 4 squared plus 1 squared. What does that give me? Square root of 26, good. And then we'll do the magnitude for B. So we have the square root of 2 squared plus 2 squared plus 1 squared. It is 9, which is, yes, the square root of 9, which is 3. All right, so over here, let's put it all together then. I'll scoot this over. Well, I will. I don't have to grab it all. Okay, so we're going to have that the cosine of theta is equal to negative 13 over square root of 26 times 3. I think I'm going to put the 3 in front of the square root of 26. All right, so how can I figure out then theta? Inverse cosine, you got it. So we're going to take the inverse cosine of this sort of ugly looking expression. Don't rationalize anything. You're going to be taking an inverse cosine anyway, right? So you could actually do this in degrees or radians. It would be okay either way. Just make sure you realize which one you're doing it in so you're not making a claim that's incorrect. If you do this in, which one do you, let's do it in radians. We usually work with radians in calc, so let's do it. What's the radian measure? And it'll be an approximation because even if it is really 90 degrees, your calculator doesn't spit back out at you pi over 2, right?
That's negative 13.
Thank you. Forgot my negative. Okay, so what are we going to get for the inverse cosine of negative 13 over 2 square root 26 in radians? I have 5.9. No? Do a typo? Yes?
Did you guys say the same thing?
Oh, I thought you said just 2.9. Did you say 2.59? I apologize. I didn't hear the 5. Okay, 2.59 then. So we match. That's great. Is that pi over 2? No. Approximately what is pi over 2? 1 point something for sure, right? It's about 1.57. Okay, it's about 1.57. 2.59, this is not equal to pi over 2, which is really the only issue that we were trying to deal with. And so because it's not pi over 2, what does that mean? It is not orthogonal. Now, we still don't know if it intersects or if it's skew, but we weren't asked to find that, right? We were just asked to decide if it's orthogonal, and it's not. So the answer to the actual question asked is that it is neither. All right, any questions on that? Okay.